My Node.js is a bit rusty. Replacing an internal Node.js module with a native Rust module made a 25x Perf boost. Let's understand why. September 3rd, 2023. And by the way, it's only September 6th, 3 days away from the big day. You know what I'm talking about? The big day? You know what day I'm talking about. This blog post has been residing in draft mode for quite a while now. I finally decided to just publish it. As such, a few things might be a bit off. But that's life, yeah. Always just share. Stop worrying so much about if it's the perfectest. Back in 2020, my team at Wix launched a new internal product, sorry, I lost my place, called a CDN Stats. As the name suggests, CDN Stats is a platform that displays and aggregates data and statistics derived from the Wix CDN. Okay. That same year, I delivered a presentation about an experiment I conducted. This experiment, which involved rewriting a single module into a native Node.js add-on using Rust, resulted in a staggering 25x performance improvement. Awesome. 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 This platform empowers front-end developers at Wix by providing real-time data on the usage of their compiled assets by our customers, including platforms, downloads per platform, response size, transfer size. These metrics allow front-end developers to identify which bundles need optimization and the urgency of these optimizations. It helped us rectify a critical issue that we might have otherwise overlooked. Due to a human error, one of our primary JavaScript assets ballooned to 33 megabytes. That's so much shitty code. Like, how do you even get that many code units? Like, minified JavaScript per character is like one of the most dense semantic languages ever. How do you even accidentally do that? Because it inlined uncompressed as a savage without, oh, okay, well, I didn't read the next sentence. I didn't read the next sentence. This actually makes perfect sense. Without externalizing it or even dynamically importing it. Okay, that's a big savage. Why do you have a 33 megabyte savage? That also doesn't make any sense. Or maybe 32 megabytes. This project seems fairly straightforward, doesn't it? All we're doing is counting and summing up values. Toss in some indices in a database, present it with a data table, and voila. But is it really that simple? Nothing is that simple. Even the most simplest projects aren't simple. How does that work? In order to populate the data table, we need to sift through the CDN logs. These are tab-separated values. Oh, nothing like a good TSV. If you're not getting patted down by the TSV, what are you really doing in your life? You know what I mean? What are you really doing? Let me guess. Dot split considered harmful? Is that the answer? Because you know what they're going to do? You already know for a fact. They're going to like dot split, decompose. I mean, the amount of garbage they're going to create is incredible. We're talking about 290,000 files per day, which can amount to 200 gigabytes. Okay, so every day we download the TSV files from the previous day, parse them into meaningful information. I'm surprised you don't just stream them out. You know, seems like a good day just to stream out those SOBs. Just because the downloading them all at once seems like that would just be the largest part. I'd be shocked if downloading them took less time than processing them. So every day, we allowed the TSV files from the previous day, parse them into meaningful information, and store this data in our database. We accomplish this by enqueuing each log file into a job queue. This strategy allows us to parallelize the process and utilize up to 25 instances. That's an odd, like, hard number to put in there, to parse out the log files within approximately 3 hours each day. I also have another question. Why not just have one big ass instance with a lot of cores, and instead of having like 25 individual instances, why not just run parallel? You know what I mean? We just learned about parallel, the GNU utility. What's an ass instance? I'm not sure where you got that from, to tell you the truth. I was ready to follow that joke to the end. I was gonna take it and run with it as fast as I can and really lean into the ass instance. But I just couldn't see it. I could not see the joke, and now I'm emotionally scarred. Then, every few hours, we generate an aggregation for the previous week. This process takes around 1 hour and is primarily executed in the database using Mongo aggregation. That's me shedding a tear for Mongo aggregation. Mongo aggregation! Don't get your things in the wrong order, because we're gonna screw you. MongoDB query was pretty intense. Okay, let's check it out. Let's check out. Anytime you can tweet out your Mongo query, you know for a fact it's going to be great. Okay, that's just, what is this, Tokyo Night? You're just showing me your Tokyo Night theme? Okay, not impressed. Not impressed. So what's the problem? Parsing gigabytes of TSV files might seem like a tedious task. Sounds like a computer task to me. Investing so much time and resources on it, well, it's not exactly a joy. To be brutally honest, having 25 Node.js instances running for 3 hours to parse 200 gigabytes of data seems like an indication that something isn't quite right. Agreed. Completely agreed with this, because I can't figure out why that's required. Like, someone said, well, isn't something about I/O tasks, blah, blah, blah. How long do you think it takes for your disk to shell out 200 gigs? How long do you think it takes for two computers sitting on the same network to shell out over the network, create the space, and update you as they come in? Like, it's going to take a while, but not 3 hours. I'll tell you that much. It's going to be in the order of seconds. 10 secs. Ooh, this is an Arch user channel, okay? We don't talk about secs around here. 6.9 for 20 seconds, right? The solution that eventually worked, I would just assume in the order of seconds. Maybe 1 minute. You know what I mean? Like, it's going to be a short amount of time. I would not expect hours. Like, if you saw hours, something's just wrong. The solution that eventually worked was not our first attempt. Initially, we tried using internal Wix serverless framework. We processed all the log files concurrently and aggregated them using promise.all. Isn't that delightful? However, to our surprise, we soon ran into an out-of-memory issue. Really? You're telling me you didn't see 200 gigs being a problem? Even when using utilities like plimit to limit ourselves to just 2 jobs in parallel. Plimit? Why not just parallel, dog? So it's back to the drawing board for us. Our second approach was involved migrating the same code verbatim to a Wix Node.js platform, which runs on Docker containers in Kubernetes cluster. We still encountered out-of-memory issues, leading us to reduce the number of files processed in parallel. Eventually, we got it to work, however. It was disappointingly slow. Processing a single day's worth of data took more than a day. Clearly, this was not a scalable solution. Reasonable. So we decided to try the job queue pattern. By scaling our servers to 25 containers, it's weird that they just, shouldn't you just put N, a configurable amount of containers? We managed to achieve more reasonable processing time, but we can truly consider running 25 instances to be reasonable. Not on this. This just seems crazy. Every part about this seems crazy. I'm glad that he recognized right away. Perhaps it's time to consider that JavaScript may be the problem. You know what you could do? A really simple thing to do is, here, I made something last night. That I've kind of been working through that I think is a really good way to look at it. This is a server in which it's very, very simple what is happening. Let's see. What is it called? Shooter. Okay. It's very, very simple. I have a cargo task that runs, and I can say how many parallel jobs, that's the queue parameter, and how many total games should be played. Then I run the server over here, and the server just logs out some basic data, or I can run it with the inspect flag to see what's happening. When I do that, this is what I get. So no matter how much I scale, how many concurrent games being played, I have a whole bunch of idle time on here. And not only do I have a whole bunch of idle time, I also have huge, gigantic garbage collection things that happen. And so you can kind of see that you're running up against a potential issue here. And the issue is not anything other than JavaScript itself. I know how to get rid of most of these idle times. And guess what? Guess what the answer is? Don't use a promise. You have to be a little bit more clever about not using this. Isn't that shocking? It's shocking to me, at least. Anyways, perhaps it's time to consider that JavaScript may be the problem. There might be certain issues that JavaScript simply can't solve efficiently, especially when the work is primarily CPU and memory bound, areas where Node.js does not excel. But why is that so? Node.js is a garbage-collected VM. Node.js is a remarkable piece of technology. It fosters innovation and enables countless developers to... All right. Can someone get me a flag on play, unnecessary dick riding? V8 determines when to free up memory. This is how many languages are designed to optimize the developer experience. However, for each application, explicit memory usage is unavoidable. Let's analyze what approximately transpires when we execute our simplified TSV parsing code. For await, ooh, nice, an async iterator. Well done. Const line, read line of stream. Const field, split. You've just created a bunch of pointers. HTTP status, numbers, that. If status is less than 200 or greater than 299, continue. I hate your lack of squirrelies, but whatever. Records, push, path name, this, refer, that. Okay. Yep, we see what's happening here. The code is quite straightforward. By using a read line, we iterate through the lines in the field, and let's see. in a stream to circumvent memory bottlenecks caused by reading an entire file into memory. Yep. For every line, we split it by the tab character and push an item to an array of results. Really, you're not really circumventing pretty much anything here. You're going to take most of that line, you're going to recreate it into these files, and you're going to hold on to it. And guess what's going to happen? You're going to still blow your stack. You're still going to use too much memory. But what's happening behind the scenes in terms of memory? Line.split is invoked, and we get newly allocated array containing multiple items. Each item is a newly allocated string that occupies memory. So this is not technically true. What likely is happening is because it's using a substring, it's actually going to be a rope string, right? So it's going to be a rope. So it's going to be a pointer. It's going to be a fat pointer. You're going to get an offset and a length, or not even a fat pointer. Yeah, it's like a fat pointer. You're going to get an offset and a length. That's all you're going to get for this, and that's effectively what's happening underneath the hood. This is in a way that array.split works. It creates a new array and strings every time. It creates new array and new string references every single time. Absolutely. The intriguing part here is that line and fields won't be cleared from memory until the garbage collector determines it's time to do so. We find ourselves with RAM filled with redundant strings and arrays that need cleaning. It's hardly surprising that our computer wasn't thrilled with this situation. Yes, you'll still use a lot. You'll still use a lot of stuff. Finding comfort in Rust. As an intermediate Rustation, I do have a fairly successful open source project written in Rust called Phenomenon. I'm well aware that memory management is one of Rust's key strengths. The fact that Rust does not require a runtime garbage collector makes it suitable for embedding within another language and virtual machines, positioning itself as an ideal candidate for implementing such a feature. This is true. Anything that manual memory management is ideal, especially for this environment, because Node requires you to have some sort of lifetime, an implicit lifetime to your memory, whereas Rust requires an explicit one. So it's able to manage all the memory it uses kind of inside of its own little world and just give out what it doesn't need to hold on to anymore. And the Neon API is actually really slick. The Neon API is super slick. I've shared a few tweets expressing my beliefs. Building applications in Rust is powerful, but the ability to embed Rust in a battle-tested VM without altering the rest of your application is a true game changer. I agree. This is actually a really great point right here. I love this point. Creating a service in Node.js and only using Rust when necessary can help you accelerate development and replace modules with more efficient ones as and when required. Using Node.js as the entry point of our application enabled me to leverage Wix standard storage database connectors, error reporting, logging, and configuration management without the need to re-implement these on the Rust side. This allows me to focus solely on what matters most, optimizing the slow part. Let's go. Let's go. Fortunately, embedding Rust in Node.js is a breeze thanks to the Nappy RS, an excellent Rust library. I think now it's called Neon. I think Neon's the one that people use at this point. That facilitates seamless integration between Rust and Node. You simply write a Rust library, use some fancy macros, and Viola. He loves that term. You have a native Node.js module written in Rust. All right, let's see what we got here. Correct, Rustations and Rustling. So one thing that's different about Rust, I don't think I honestly don't think you're actually using that much less memory with Rust here. I think it's getting rid of the memory you're not using that's really helping out here. And plus, there's a whole bunch of like pointer cost in Node.js that's just not present in Rust. Let's see, I can begin by declaring my structs as irrelevant data structures I want to parse into a type-driven development workflow. I start with a record, the most basic line I want to parse from the TSV record set. Instead of designating every part of the record as a string, an owned string, I can force into a reference. Yep, there you go. Bada bing, bada boom. This is a fat pointer, right? It contains an offset and a length. Note, by making record contain slices of string with an A lifetime, we're essentially stating that record is a derived data structure that doesn't alter the original data. That implies record cannot outlive line, an advantageous feature. It aids us in developing our application while being mindful of optimal memory usage. All right, so let's see what they do there, because I'm wondering if he does something different here. Is there some sort of thing? Oh, someone's saying that I'm pronouncing something very wrong. Viola is French, actually. The way he's pronouncing it is something really wrong in Spanish. Oh, really? Well, Viola, these nuts. Have you thought about that one? All right. To maximize our capabilities of browser caching, static assets, and deployments of... Oh, hold on. Oh, yeah, that's where we're at. However, merely deriving the raw data isn't sufficient for our use case. To maximize the capabilities of browser caching, static assets are deployed with a content hash as part of the file name. Instead of having artifact.file.js, we have artifact.file.abcd hexadecimal.js, files allowing the browser to cache them indefinitely. Okay, nice. For our aggregations, we want to remove this content hash. Furthermore, we want to infer the artifact name and the path name. This is why we introduced enhanced row. Enhance! Let's see, okay, path name, refer. I'm surprised you didn't use a path buff, artifact, or a path, or whatever one is the equivalent of that. File name, a cow. Ooh, nothing like a cow. You know for a fact that once you get to a cow, you've reached new levels of rustationing. They could use some power peg in this code. They could. As we can see, enhanced row incorporates everything that a record A does, but it enhances it with a few values. Artifact, a reference part of the path name. File name is a copy on write. Just as we mentioned, we attempt to remove the content hash from the file. If we don't find the content hash, there's no need to copy the string. If we do find it, we copy the string. This type allows us to be incredibly explicit with our intentions. Yep. After defining these two structs, we implement a try from. Okay, I love a good old-fashioned try from. And a try from record. Oh, beautiful. I love try froms. This is like one of my favorite features of Rust, is the trait system and its like ability to include on any type and just make things feel very standard. I love this part. I love it. I love the fact that there's a good Rail type programming when it comes to basic operations. And try from is one of those like kind of like, here's the rails, just go on the rails and use what we've already provided. I love from and try from. I use it all the time. Next, we create a new struct called resource counter, which performs aggregation for our given files. It's a simple wrapper around hash map with our key composed of artifact file name. Okay. Resource counter allows you to provide an enhanced record and it only clones the data if necessary. And okay, I want to see what that is. Can we see what that is? Because what I'm seeing here is something much, much different, actually. Are you guys seeing this? Are you seeing what's happening right here? So what's happening is that enhanced row relies on the lifetime of a line. But if you look at this JavaScript right here, the lifetime of a line is actually the entirety of reading the stream. Right? So the stream itself goes on and on and on, which makes me think that what I'm seeing is two very different implementations. I think you could have got a much better performance in JavaScript doing what they're saying right down here, which is to add a map as your like counter, and so then you're only counting on certain specific items. You're not recreating a record every single time. This is like a classic JavaScript oopsie daisy, which is that it's so easy to create memory that you write shit awful all the time. Right? And so if you were trying to build the exact same thing in JavaScript, I don't think it's hard. I think that they're just simply missing this one little thing. So let's find out. With this, our code was complete. However, since we implemented a performance optimization feature, we knew we couldn't call it a day without benchmarking it against the current JavaScript implementation. This benchmarking would require us to use Node.js module rather than using a Rust as our CLI or something similar to ensure we included the overhead of Rust to JS communication. I fired up our internal JavaScript benchmarking tool called Perf and wrote a simple benchmark. Ba-da-da-ba-ba-ba. Native parse async, some big feature. Okay. Some big fixture. Run async native parser, okay, benchmark node, create file stream, some big fixture, const values, await JS parser, let's see, run async this thing, all right. It ran, and the results were impressive. Okay, that looks nice. That looks nice. Now, but again, what's this thing right here? Why is this happening? Again, I'm telling you, it's because of this line right up here. It was a simple wrapper around a hash map, and our keys was composed of artifact file name, and our value had a counter for the request based on the platform. I think it's literally this. I think this is one of the big differences, is that you're only storing unique combos of artifact and file name and an associated int. So you're really storing a very few amount of pieces of data, right? You're storing some megabytes, right? Yeah. Okay, so someone's saying, like, show me what's going on here. So this is how I read what's happening right here, is that we have something that looks like this. So, right, they had four await const item in stream, right? Or, sorry, of stream, right? That's effectively what they had. And then they would do they'd had something like this, const out equals an array, and then they did out dot push some object in here, right? Can we all agree? That's effectively what they were doing, right? This. So what they're doing in Rust looks a little bit different. They're doing something that looks more like this. Const out is this, and then for await. Well, really, it's I mean, it's a new map, right? Let's just be fair here. For await const item of stream, and then doing some sort of out.set or out. We'll call it some sort of set. You know, item. Let's see, some sort of combo, right? Item.id, item.path, or whatever it was. I forgot the exact name. Hash. I forgot what they had in there. Equals out.get this thing plus 1 or whatever it was, or 1, right? They had something that looked like this, right? Right? That's effectively what they're doing. And so these are very, very different. Notice that you're recreating the line every single time and storing all the information versus just storing all the information using a hash map. So that way they didn't have to create an individual object every single line. Instead, they just mutated a variable or created one new entry or X new entries into a hash map. It's an apples to orange. Yeah, there's definitely something going on here that I think is vastly unfair to the comparison. At least that's how I read it when you say things like that. And I think that's why it makes sense. You see these two vast differences, is that Rust should not reduce memory by 300-fold. As far as I can tell, when it comes to a bunch of string and number storing, it can usually reduce the size by like up to like 4 to 5 times, right? It can be like definitely smaller because you can just store things in such smaller amounts. But this is just like straight up saying no way. No way, not believing it, right? Also, Node itself takes up 40 megs, right? Like just the environment. What I mean by that is if you go like this, go node e while true, right? There you go. That thing's just running VMRSS. Like it just takes up 40 megs, right? So this is how much memory it's taking on my system right now. So it's like a forever running item. It just runs forever. Yeah. If you're testing, yeah, you have to be careful what you're testing. I have never seen something do this. I've seen people change stuff, but they said they launched Rust as a module from Node, so the overhead would still be there. Yeah, they must be memorizing, or they're just measuring the memory used by this. I'm not exactly sure how they're doing the memory just by the native module, because it, like you said, it should be wrapped up inside of here. It should be a minimum of 4 to 3 megs, right? There's something going on here that I think we're goofing up a little bit. You know what I mean? Something's wrong. I don't know what it is. Let's look at these ones. JS parser, let's see, runtime. All right. Memory, awesome. This. Another thing that I'm actually a bit surprised by is this right here. The standard deviation, I feel like should be a lot larger. This seems reasonable, I guess. Anyways, the results were as follows. JavaScript parser, a lot of milliseconds, this much time, that much memory. Rust parser, that much, this much, and this much. Yeah, again, I think it's just simply the data structure you chose. While there's significant difference in times, the most glaring disparity lies in memory usage. The difference enables us to process more files in parallel, and that's a huge advantage. The Wix, I like them using Rust, though. I'm thinking Rust was a better move no matter what, but I'm just saying this comparison might be unfair. The Wix deployment preview model is based on an ephemeral Kubernetes pods. Remember when Eazy-E tried to describe Kubernetes because of that Cameo payment? I've never been able to find the video again, but I loved it. If someone can find it for me, I would be so appreciative. Pods that can be manually requested for a specific commit. The ingress proxy can direct traffic to these special pods given a specific header. This is great for testing something as innovative as this project, so we decided by running a few preview deployments using the Rust parser instead of the JavaScript ones. This is also great. It sounds like you can also do shadow traffic comparison, prove that your new feature written as a whole new rewrite can also, is effectively creating the same information. It also is really great. I really love the idea of being able to compare things in a real environment. You know what I mean? Not just some benchmark ran on some person's computer, but like a benchmark as in we have all of our instances running this and we have all of our instances running this. Let's see which one's faster. Let's see which one uses less memory. Let's see what we can do here. I love that idea. We ran a benchmark a few times and processed the same 190,000 log files using the following infrastructure. JavaScript implementation with 25 instances, which finished in 3 hours. Rust implementation with 1 deployed preview instance completing in 2.5 hours. This does not include any database I/O since the deployment preview instance is read-only, but there are fewer insertions in the Rust implementation because we can process more files simultaneously. This enhances our aggregation and reduces the number of records to be pushed to the database. We could modify our implementation to store data directly in a simple storage like S3 and then have a separate job that transfers the data directly to the database. This would allow us to separate computational work from network work. Nice. Assuming the times were the same, the Rust implementation used only 1/25 of the resources available to the JavaScript implementation. That's 2,500% performance boost. Even if we do need to add the MongoDB insertions, which may take extra time, we would still be looking at a boost of 20,000 or 2,000, 19,000%. Gosh, I keep saying 20,000, 19,000. 2,000, 1,900%. Either way, that's a significant win. I agree. I completely agree on this. Plus, you can still parallelize this. So what's the takeaway? It seems that choosing the right tool for the job is essential. Also choosing the right data structures. Okay? That data structure call out is very serious. Okay? I think we really got to focus on that data structure there. Some tasks are well suited for JavaScript while others are not. Although Rust is a language that's more challenging to master, we can still encapsulate the logic and distribute it in such a way that users don't mind using it. We can see this trend across JavaScript ecosystem. Next.js replaced their use of Babel with Swisk and may use TurboPack by default. Fingers crossed. I assume they're going to be doing it soon. ESBuild, a popular choice for bundling and transforming TypeScript or modern JS to JavaScript, is written in Golang. It's simply faster, which is always beneficial. Yeah, it's massively faster than TSC. It's beautiful. I suppose my takeaway here is use whatever makes you happy. And if something is too slow, profile it first, then encapsulate it, and then perhaps consider writing it in Rust. I do like the idea of profiling it. We never knew what was slow. So he never actually profiled it, right? He only timed it, right? He said, okay, it takes 25 instances and takes 3 hours. That's not profiling. That's timing it, right? What was slow? Why were you running out of memory? Like, none of those questions were answered. I would highly recommend always asking those questions. I think it's very, very good. And lastly, I want you to go on Twitter, and if you would like, you can give this person a follow. Oh, he follows me? Look at that! Hey, that's a good article, though. I really did like it. I would really love, if you could whisper me what happened and what you changed, I would love it. I would love to know if you did change data structures and if it's fair to say that still at this point. Anyways, the name is the Primogen.